All right, tonight's agenda, we are going to look at the standards here in this particular unit. We're going to focus in on the physical science standard. We are going to talk about the engineering project as well. Towards the end of the unit, we are going to look very briefly at the unit outline and the teacher walkthrough, and then Matt and I will kind of take you through each task set. One of the activities does lend itself to being transferred to virtual, so we are going to actually do that activity with you. And then we will participate in that reaction sort activity, which is a really great way for students to learn about the different reaction types. And then hopefully as we get ready to conclude towards the end, we'll talk about the water quality project, and then we'll look at some assessment examples and a rubric. We are in the process of getting some more professional development, all the patterns teachers around assessment. And so, these are some examples, but they are likely to probably be changing in the coming weeks, just a heads up on that. All right, so this is our Unit 5 webinar on chemical reactions and pollutants, which is the phenomenon or the theme that we are focusing on in this particular unit. And so Matt's going to talk to you a little bit about our roadmap.
Yeah, it's just me a quick overview and then we'll get into it. I'm actually going to start with task set 1. The focus is pollutants, and that's going to be introducing us to the theme for the unit. Students are going to learn how to categorize different types of reactions, how to balance equations. The main kind of lab for this unit is called predicting products. And then the engineering design project that ties us together is called water quality engineering. And then I skipped resource management. That's what we're going to start with first. And that is something that Joe May will talk about, but it's flexible where it fits in this unit or potentially elsewhere in the year.
All right, so let's talk about our physical science standard here. So the main standard that we're working on in this particular unit is actually a continuation of something addressed earlier in the year. This one is construct and revise an explanation for the outcomes of the chemical reactions based on the valence electrons and patterns in electronegativity. And so, knowing the patterns of the periodic table is something that, students focused on and worked on earlier in Unit 2. Now we're kind of bringing that back, those electronegativity values, those valence electrons, and really now trying to have students put that together with all that they've learned in bonding also, and be able to predict the outcomes of chemical reactions now. So as we're looking at this particular standard, constructing and refining the explanation is what you will see as the main practice. When we look at the disciplinary core ideas, again, this PS1.A, that is the part that was probably focused on more in Unit 2 because it's really focusing on the arrangement of elements on the periodic table and then the patterns, repeating patterns that are formed in that area. So as we're coming back to this standard now again, we're really focused more on this PS1.B, which is the chemical reactions piece. And so not only are we wanting students to be able to predict products, but we also want them to be able to balance chemical reactions to show conservation of mass. And, I think it's really an easy thing for students sometimes to grasp how to balance the reactions, but knowing why they're doing that, and tying that in with conservation of mass is really important as well. And so our main cross-cutting concept here is patterns. Again, patterns in being able to look at how reactants break apart and then recombine into their products based on their electronegativity values and their valence electrons. And then here, we're going to just take a quick look at the unit planner and the teacher walkthrough. So the unit planner is linked here. Of course, you can also find it on the Patterns website. If that is more convenient to you, you can also find it in the Google Drive. So lots of different ways to access. We tried really hard to, clean up the files in this particular unit because we found that, there were a lot of duplicates of things and things not in the right folders. So hopefully as you're navigating through, you'll find that to be a little bit easier. So here is the unit planner, and the unit planner just starts at the top always with, kind of saying what our phenomena is, what our, unit essential question is. So again, we're really focused on pollution in this particular unit. And so we really want to look at air and water pollution because those reactions are related to one another. And it also allows us to address all the different reaction types if we look at air and water pollution. And so that's the anchoring phenomenon that we're focused on throughout the unit. And so the unit essential question is, how are pollutants produced and what are their chemical consequences for our air, water, and our climate? Because that's another idea that we're going to be recirculating back to, is climate change and impacts of climate change in this particular unit as well. So here we have our two main standards. So we've already talked about the physical science standard. And then also, as we get into the engineering project is really utilizing this engineering standard where students are really looking for a solution, doing research to find a solution to water contamination and, trying to figure out what is the best way to be able to remove contaminants from large amounts of water, not small amounts of water in this particular case. So as we go through the unit plan here, we see that we have kind of our task set 0, which is our tribal studies lesson. This is a lesson we're going to talk about a little bit more that's required by Senate Bill 13, I believe. It is placed here, but could also go in other units, and I'll talk about that in a little bit. Then we get into task set 1. Task set 1 is always our unit opener, right? So students are engaging with just looking at different kinds of pollutants, thinking about what kinds of chemical reactions create these pollutants, but then we also use chemical reactions to remove pollutants as well. So can be a double-edged sword there. As we get into task set 2, that is the reaction sort activity. So that's students' first introduction to what are the 5 reaction types. And you all will do this activity a little bit later. So they'll be able to self-discover those reaction types in task set 2. As we move on to task set 3, this is where students get into learning to balance equations according to the law of conservation of matter. Matt and I really feel like it's easier for students to learn to balance chemical reactions first before learning to predict the products. We feel less confusion with subscripts and coefficients that way to do the balancing first. But many teachers do the balancing after the predicting products as well. And then task set 4 is the predicting products lab. So that's where students are engaging in a lab. They're looking at those electronegativity values, observations, thinking about the patterns that they saw in task set 2 to predict the products of chemical reactions. And then after that is over, you move on to the water quality project. We still continue to work on this project to make it a little bit more accessible and affordable for teachers, and we'll talk about that a little bit more later. And then last, we have some assessment examples that I did some revisions to. But again, we're going to be getting more information on assessment, 3D assessment this week for all the patterns teachers. So definitely look for some changes to those happening in the next few weeks. So at the top here is the links to most of the important resources. So you'll also see the unit walkthrough is there as well. The unit walkthrough has most of the same information that we've just talked about. It's just that the unit walkthrough also will kind of give you a 1-sentence summary about what students will be doing in that task set, what we want them to get out of that task set. And then as you progress through the task sets, it will also tell you like what they should know from the previous task set. So it's a nice kind of, couple page resource to just be able to see the whole flow of the unit from start to end. And then again, if you're thinking about rearranging lessons or, flipping things, just, keep in mind that, the lessons are arranged in this particular order. And so they, they build on each lesson as we go through. So that's a little bit about the Unit 5 walkthrough. All right, let's go back to the slides. And so now I want to talk a little bit more about that tribal natural resources, TS0, that is there at the very beginning. So this is a lesson that's created by Oregon's Native American peoples on resource management. Again, it is part of Senate Bill 13. And so Senate Bill 13 does state that these lessons that have been created by Native people, they do need to be taught as is. They cannot be altered from their original state. So you'll notice that this lesson, looks very different than a patterns type of lesson, but that's why, is because it's cannot really be altered. It can be augmented, so you can add to it, but you just cannot take away information that was placed there by the Native people. And so if you'd like to learn more about Senate Bill 13 and the Tribal History Shared History webpage, we've linked that right here for you so that you can see information about that. There's several different lessons. If you teach patterns biology, several of the lessons fall into patterns biology. So this is one of the ones that, you know, we are trying to help share that load of teaching these required state lessons and implement some in chemistry as well. So in this particular lesson, students first start with learning about the history of treaties, how they were terminated, and then how the federal government restored recognition of tribes. So it does start as a little bit more of a history lesson, but then it kind of evolves or transfers into how Native people are managing their land now and how they've managed their land since time immemorial. And then also it looks at what current projects the local tribes are working on. And so there's a website that kind of links to all the tribes. And so certainly you would want to be looking at the ones that are in your particular area so that students can be learning about the work that's going on to do land and resource management. So the flow of the lesson is that first you want to start with that historical background, and then students go on to read about the termination and restoration of tribes, and there's a graphic organizer that accompanies that. And then students go to the website where they are investigating. And so one way of looking at how all the tribes are working and facilitating different projects right now is to have, you know, different groups look at different tribes throughout Oregon, look at what they're currently working on as far as land and resource management are considered, and then have them be able to share that back out with the group. So this is kind of a standalone lesson. It is, I would not say directly tied into air and water pollution, although it is about land and resource management. And so it does tie in with that. Also, you know, we have done this lesson when we have been talking or doing our nuclear unit, because in our nuclear unit, we do really focus on the contamination in and around the Hanford site in Washington and how that has negatively affected the soil and the water there. And so, you know, we felt like it was a good fit there as well. So I think going forward, we're going to put the lesson in either spot, and then people, you know, can choose what they feel is their best place to put that lesson.
Yeah, and just to add a little bit, it could also go at the end of this unit. We're putting this as task set 0 so that it's kind of like front of mind for people when you're planning. Yeah, but it's definitely very flexible.
Okay, so now we are going to go on to talking about our task set Unit 5 opener. And so the set of slides that goes with task set 1 really introduces this idea about pollution. It asks students what they would like to know about pollution. I really like this graphic that shows primary pollutants and secondary pollutants. And this is why we really wanted to tie together the air pollution and the water pollution, especially because the nitrogen and the sulfur gases mix with water in the air and then form sulfuric acid and nitric acid, which comes down as acid rain. So, you know, those two things, you'll see those themes and those reactions kind of coming back up over and over again. But again, with the unit opener, our goal is for students to write some questions that help drive the unit and that will be answered as they go through their learning in the unit. So I just put some example questions down here about that students may generate or may come up with. So how do fossil fuels create nitrogen gases? You know, how are sulfur gases transformed into sulfuric acid? What conditions are needed for ozone to form? These are different questions as they're going through the unit opener and they're watching the videos and looking at the information in the unit opener. I think would be plausible questions that they come up with. I definitely feel like for the unit opener, I always feel like if I give an example or two of what a good question is, then I usually get much better questions back. So I think that's always a good idea to throw out a few ideas for questions and then have students write their own questions. You'll probably get better questions that way. From there, after students have kind of populated the driving question board, then they are going to dive deeper into these primary and secondary pollutants. So there's kind of two choices here at this ending part of the task set. They can either use the existing slides in the slide deck that talk about each primary and secondary pollutant and have some information on each. So they can kind of use that. And then they can, or they can read the articles that are in the pollution text set, and they could create their own set of slides. Obviously, that's going to take a little bit longer. So I think that that's going to depend on how long your class periods are and, whether you would want to spend more than one class period or not, doing the unit opener. If you decide to use the existing slides, then once the students write or read the article on the pollution text set, they could write a summary to accompany that as well. So it just kind of depends. Do you want kids to make their own slides? Obviously, that's going to probably stick with them a little bit more if they're doing research to create their own slide on the primary and secondary pollutants. Or do you want to, just have them go through that information and then read the articles on the pollution and have them write a summary? So again, just think about the timing and how much time you want to spend on that. I generally don't want to spend more than one class period on the unit opener. So, I tend to shorten that and have them read the pollution articles and write a summary. All right, now I'm going to stop sharing. I'm going to let Matt take over because Matt is going to take you through task set 2.
Cool. Thank you. And I used to be really good at Zoom, I like to say, but not. It has been a while. Awesome. Cool. Okay, here we go. All right, so we're going to transition to a card sort activity that we're going to do in breakout rooms, but a brief transition before we do. When students were introduced to primary and secondary pollutants, as Joe may mention, that's a way for us to introduce students to a wide variety of different types of chemical equations or chemical reactions. And so our next task is going to be sorting those. And so I would say the main learning goal of sorting is to better understand the rearranging that happens in chemical reactions, putting them into different categories can help to do that. So I'm going to show what I'd like for us to do first. So if you have the slides open, would you click on the virtual card sort activity that's linked in here? And I'm going to use one of the sets of slides for group number 1, just to talk through our instructions of breakout rooms. And then we're going to send you into teams. We'd like you to get the experience of doing this activity similar to what students would do. Both Joe May and I do this with physical cards, but you'll be doing it digitally. And then also just a chance to interact with other teachers. So there's going to be time for introductions and things like that. So once we send you to breakout rooms, and we're going to be in groups of either 3 or 4 today, then I'm going to ask you to click on the group that matches your breakout room number. We didn't know exactly how many to expect, so I have 10 groups, so it's a little more than we need. So the very first slide has instructions for introducing, and just would you take time to introduce yourself to your other team members, including the things that are saying there. And then the note on the bottom says, after introducing yourself, consider having one team member share your screen for the next activities. It is really helpful for people to access what we're doing. If one person can share a screen, it's very likely that there's going to be someone in your breakout room that might be accessing this on their phone and not have the same capability of moving things around in the Google Slides. So if you can have someone volunteer to do that, that would be great. Then the next slide has instructions for part 1. You're going to do 2 different card sorts. For part 1, the cards that you're going to see are going to have 15 equations that include either numbers, letters, or emojis. And your job is to work as a team to sort the equations into 5 different groupings, come up with a name for each category. And if you kind of know the intended names as a chemistry teacher, could you maybe think of what might students come up with as a descriptive name? And then also write a brief description for each category. And often that can help lead to coming up with a name. Like, what do you see happening? And we're focusing on how the characters are rearranging. So there's a little note about how to work as a team. One way to do that is to have each person sort, in this task, a different type of card, sort numbers or letters or emojis, and then talk as you do it, and then discuss the names for the category. And then you'll see there, hopefully you're able to move around in the slide and grab those things. There's the places for the 5 categories. And then instructions for part 2. The next part's going to have chemical equations, and your job is to sort them into the same categories that you created in part 1. So go ahead and retype the name for each category into the 5 text boxes on the screen. Sort the chemical equations. I just had this realization. I hope this is edit access for everyone, but if not, I'll fix that. Sort the chemical equations into the same groupings as part one, and then keep note of any that you're unsure about. And so just think of a way of splitting it up so that different people get to move it. Usually in class, I physically have students take the stack of cards and just like divvy them up, and then they're moving them around and discussing, especially review each category after you're done. And then after you've done that second card sort, there's a few questions for you to discuss as a team, and we'd love for you to write your responses in here. I won't read those to you right now, but it's just a way encouragement for you to be able to talk together. And then lastly, when we're done with this and we come back all together, I'm going to ask each of your teams to be ready to share something, your answers to one of these questions. So it can be any of your choice. And then depending on time, we might get every team a chance to share out, or just the teams that are interested in doing that. But if you can kind of focus on one. I notice I have a couple things in the chat. I'm just going to double check before. Perfect. Awesome. We're good to go. So I'm going to send you to breakout rooms. They are going to be at random, and they give me like, during COVID, I was good at doing this. I think I'm going to actually stop sharing. I lost track of what
Go.
Cool. Awesome. Okay. Well, welcome back, everyone, and thanks for the break. I think I originally was intending for people to have a chance to share out, but I'm trying to monitor time and just make sure that we have enough time for the things that we have left. And so I think, I guess I didn't ask you, Jomei, but to move forward on the next thing, does that sound good? So
sounds fine to me. We're going to have time we want to make sure there's time for questions at the end. So if you want to ask more questions about that activity, we can talk about it at the end.
cool. So on this slide, I have an example. I'm going to show full screen. Here we go. I have an example of a student like whiteboard and the names that they came up with. So this is hard to read, but it says simple, backward, both swap, one swap, and then squared. I love, a lot of teams said something like distributive, or that was like a word I was looking for specifically, like for the combustion type reactions. Yeah, and I'll say just kind of the question I think I heard was like, what do you have students do with this? And that's really, so like after students sort the first set of them, then at least in my classroom, then we give students like the actual or names, like single replacement or single displacement, depending on how you say it, double replacement, synthesis, combustion, and decomposition. And then also have, at least for us, have a place for them to write it down. So I also heard from some of the teams just kind of summarizing that like these particular cards required students to have, or at least really, it would be really helpful if students had understanding of polyatomic ions, or at least that had been, like I said, exposure to that idea of groups of atoms sticking together. Okay, we're going to move on to the next task set, which is balancing reactions. And I plan to do this relatively quickly. We use the PhET balancing chemical equations simulation. You can click on the link if you haven't used it before, but to motivate the need for an equation to be balanced. One thing I really like, or a couple things I really like about the PhET simulation is I love that they have a physical balance so that students are thinking about the same conservation of mass or conservation of matter. And then also the drawings of the molecules on each side so that students are like getting a visual representation of what these molecules look like. And there is a link there. The second thing, it's also linked in the unit planner and the teacher notes. There's a document that students can complete to do this a bit more independently, but with instructions to help them kind of walk through that. And then on the additional resources, and these again are also linked in the unit planner and the teacher notes. But the first one, A, says counting atoms with balancing equations with molecule diagrams. That's something that the teachers at my school and our students use. And it includes drawing diagrams of molecules. So like CH4 drawing 1 carbon atom and 4 hydrogen atoms, and then using that as they're thinking about both counting atoms in a chemical formula and the balancing equations. And then the leveled practice just has different levels of practice. So for students. And then just quickly, the second half of this lesson is about the nitrogen cycle. And there's a 3-minute video that students and you all can watch as a class about the dead zone in the Gulf of Mexico that's caused by nutrient pollution. I'm losing some of my words right now, but caused by nutrient pollution. And this we're focusing in this lesson on nitrates, but it's also nitrates and phosphates causing like kind of more aquatic plants to grow and use up the oxygen, leaving less for fish and other creatures. And then the document that's linked there has equations for students to balance that are part of the nitrogen cycle, which students also get a description of what that is. They label those on the diagrams and then create their own example flowchart. And I would say this is quite an extension. This is just a lot of practice with balancing equations, connecting it to the nitrogen cycle. And then also it does link up to the idea of pollution. So, that's task set 3.
Okay, Matt, if you will stop sharing your screen, I think I will take back over. Okay, everybody, I am going to talk now about the major lab that is going on in this particular unit. So this is called the Predicting Products Lab. And so this lab, in a sense, is a little bit of a departure from the traditional patterns lab because we're not going to have we're not going to have numerical data that we graph and then, get a mathematical pattern and that kind of thing. But we still try to incorporate many of the elements of a patterns lab into this particular lab. So in this lab, students first are taking what they learned in task set 2, right? So task set 2 is what you just did when you were in the breakout rooms. It was really introducing students to the patterns and the ways that elements are, breaking apart as reactants, recombining as products, and that we saw some repeating patterns with how that was happening. We also want to bring back that information that they have learned in Unit 2 and that we've revisited in Unit 4 about electronegativity and valence electrons. And now we're really trying to ask them to put all of that information together to be able to predict the products of a chemical reaction. So in this particular lab, this is a picture of our Oregon Capitol building. It's made of marble. The wild guess is about what will happen to this building, if we continue to burn fossil fuels. Those fossil fuels are giving off sulfur and nitrogen gases that are then eventually forming sulfuric and nitric acid in the atmosphere, causing acid rain. So that's kind of where we start, right? So we're still doing a wild guess about what we think is going to happen to the Capitol building. And so students are writing out possible products that they think could occur from the nitric acid and the sulfuric acid reacting with the calcium carbonate in the marble. And then they're also tying that into what we were just learning in the previous task set, which was about like what is going to happen to the overall mass of the building based on what you predicted the products should be from this particular reaction type. Again, this is a guess at this point. They have had some pieces of information to kind of help them. I wouldn't say that it's a completely wild guess, but they have not practiced putting all of these pieces together, and it's a lot. I mean, I often tell my students that chemistry is like a journey where we are summiting Mount Everest, and when we get to chemical reactions, that's it. It's like we are trying to use all the things that we have been learning all year to be able to do this piece now in stoichiometry. So they make their wild guess. Then what we like to do, and this lab had a pretty big overhaul or, redesign last year. So, if you haven't looked at this lab in a couple of years, you probably, want to look at it again because the reactions have changed and the way that the lab is being facilitated is a little bit different. So in years past, it used to be that each group was kind of investigating one reaction type. The feedback from teachers is that they really wanted students to experience all the reaction types, right? So now they're moving through several stations throughout the room so that they are looking at all the different reaction types, not just one reaction type. And so we like to start them out with a demonstration. And so I found a little video clip of this demonstration. This demonstration is great because it is a crowd pleaser. Students like to record this one, but it also allows you to show and model for them what a decomposition reaction looks like, as well as a combustion reaction, and that gives them two solid examples before you ask them to move on to the stations and do the same with the other reactions that are going on in the room. So I'm just going to play this really quick. It's only 20 seconds, but we call this burning a gummy bear. So here we go. Oops, no, that didn't play. Let's try that again. So the teacher here had already decomposed the potassium chlorate. So you put a scoop of potassium chlorate in the bottom, and then you use the Bunsen burner to decompose that. It's going to liquefy and then release oxygen. And then you put the gummy bear in. It's better if the gummy bear has been sitting out and it's hard. And as you can see, when the gummy bear goes into this very oxygen-rich environment, it just bursts into flames. Now, it's a little worrisome to me that on this video that the test tube is sliding down as the reaction is happening. I do say that if you have a fume hood, you should definitely do this demonstration in a fume hood. It is one that gives off quite a bit of smoke and vapors and as well as flames, and it is very hot. So, but like I said, this is one of the ones that students want to record, you know, that it is really something that they probably remember about chemistry many years from now. All right, so you start with that demonstration. Now with the demonstration, you would have, let me get out of this screen and go back to full screen again. You would have some slides that accompanied the two reactions in the demonstration that were similar to this. Now, this slide happens to accompany one of the stations that students would go through, but it's just to give you an example of what students would see at each station. So it gives them a little bit of background on the chemical reaction that they are doing. Then it tells them the electronegativity values and the valence electrons of the elements that are involved. And then they do the reaction, and then so they're supposed to use that information that's on this particular slide along with their observations to be able to figure out which set or which reaction is correct and which set of products is correct here, right? So again, this is their first experience with being able to predict the products. So giving them some different options of how elements are going to recombine, and then also bringing forth the information on electronegativity and valence electrons and their observations are going to help them to be able to figure out which are the correct products. So again, you would model that with students as you're going through the burning of the gummy bear, both the decomposition reaction and the combustion of the gummy bear itself. Then there are, I believe, 9 stations that you would set out throughout your room, and those 9 stations are going to have all different types of reactions there. So the reason that I picked station 7 is that station 7 is a double replacement reaction that involves an acid and the calcium carbonate. And so this is the one that's going to help them come back at the end and be able to make their data-informed prediction about what is going to happen to the Capitol building. So the acid here is different. It's hydrochloric acid instead of nitric acid or sulfuric acid, but it's a very similar reaction to what they're going to have to predict for in the in the end of the lab. So that's why I picked that one to be able to showcase that. So they're going to go through all the stations. They're going to do all of these reactions. They're going to write down their products. Definitely as a teacher, I'm walking around, I'm checking on them as they're, like especially with the magnesium and oxygen reaction, sometimes they can think that they are seeing things there that they're not really seeing as far as the observations and what information is here. So you've got to definitely be monitoring them and checking in on them, because they don't have a lot of experience with tons of chemical reactions. So, they're going to need some help along the way. Once they're done collecting all of their data and predicting their products for the reactions, then at this point, you would assign each group in your room to creating a board for the board meeting. And so we usually do this on whiteboards, or you could do it on Google Slides as well. And they create a board like we see down here. This is the example board on the combustion about what the reaction type is, observations that are associated with that reaction type. The evidence is the different types of reactions that they've predicted the products for. And then, this is the part that really the performance expectation is asking students to do, but really explain why the elements are combining in that way. So they really need to talk about what elements are involved in this reaction, what's happening with their electronegativity differences. Do they have a big difference or a small difference? What types of bonds is that resulting in, to be able to justify why those are the products that form from that particular type of reaction. And then last, we wrap up with them returning to what that wild guess is. So here we have our reactions, our nitric and our sulfuric acid, and the calcium carbonate from the Capitol building. And so now at this point, again, they really want to go back to that one reaction that we saw happening at Station 7 to really help them think about what's going to happen as this reaction proceeds. And then this reaction also is going to produce a product that decomposes into carbon dioxide as well. And so again, we kind of get a double whammy where we get, a double replacement reaction followed by a decomposition reaction here as well. So it gives them quite a bit to discuss in their conclusion. So after they are done making their data-informed prediction, you can test this reaction in class and then, be able to provide them with an actual result and test for the carbon dioxide that's coming off of the reaction. And then they would be ready to write their conclusion at this point. Again, not a traditional patterns lab conclusion because we don't have a mathematical pattern, but still trying to incorporate as many of those elements as possible. Okay, I feel like I saw the chat.
And quickly about the supply list. I was going to find the link, but that's linked in the teacher or in the teacher notes in the calendar.
Yes, I believe we have a Google Sheet that says all of the setup, like what you need to set up at each particular station. So let me just open up that Unit 5.
That would be great.
And yeah, there's the. And so these are the teacher notes for this task set. And so if you click on that link right here, it's going to tell you kind of what you need for the demonstrations. Again, hopefully you should be doing that in a fume hood. And then all of the different stations, there's kind of two different options for Station 4. One is the decomposition of baking soda. The other is the decomposition of water. So a couple different options there. And then Matt has also linked some information about how to do this basic setup for the electrolysis of water. So that will tell you what you'll need at each lab station. And yeah, that should help you get started. Hopefully you have some student aides that can maybe help gather some of those materials for you. And then, okay, I think we're ready to go on to talking a little bit about the water quality project now. So the water quality project, I guess I will say it's been under construction the last couple of years because the two things that have been obstacles for teachers in implementing this project is that you need to do this project, you need very special like complexing ions to be able to detect and color the water for nitrates and phosphates at these very low levels. And those can be expensive and sometimes cost prohibitive. And so there's the complexing materials and the test kits also that can be very expensive. So we've been trying to figure out ways to, use alternative dyes or different. We tried using food coloring last year and that did not work well. So we're trying some other things this year. And then, yeah, so we are constantly trying to figure out how to make this a little bit more accessible for teachers. And then also the other. Let's see, the other issue, I just had it and now
Disposal is an issue.
Oh yes, disposal. Sure. Thank you, Matt.
Yeah.
Yes, the complex ions sometimes are very bad metals.
Yeah, cadmium for the ones we use, and then antimony. I will say this was one of our favorite, like students' favorite projects throughout the course of the year, and so I love it. But it is, there are challenges involved with it for sure. And
we'll talk about a couple of ideas of ways that you can maybe skirt around that a little bit. But at least at this point, I wouldn't advocate using food coloring because we did not see a lot of success with that last year trying to use that. All right, so in part 1 of the project, this is where students are kind of getting their water samples. They are detecting what contaminant is in their water samples. So depending on what version that you try to implement, Matt's version and the patterns version both have nitrate, both have phosphate, and then copper. And then I think ours has chlorine. And so, these are common contaminants that are worrisome in the water, can cause a variety of different problems. So students are doing more of a qualitative test at this point, trying to figure out which of the contaminant. And we don't actually go out to the water sources and collect samples because we really only want students' water samples to test positive for one particular contaminant. So we do all like make all the samples so that they only test positive for one particular contaminant. So they determine the presence of that contaminant, usually from a test kit or a basic chemical reaction. And then they spend a little bit of time doing research to figure out what are the sources, like where does that contaminant come from? How does it get into rivers, lakes, streams? And then also what effects can it have not only on the environment, but also on living things. So this part one usually takes 1 day. And then part two is the Beers Law part of the project. And so this is, where a lot of our like revisions and trying different things are coming from, because this is the Beers Law part is where you need some of those complexing ions. And again, those can sometimes be very heavy metals to be able to turn a color so that a colorimeter can detect the concentration. So we do use vernier colorimeters. Spectrometers, of course, would work as well, but the colorimeters are less expensive. Also in biology, they use the colorimeters as well. So, we share those. So that makes it a little bit more cost effective to do this project. But students are given 4 samples that the concentration of the sample is known. And so they put those samples into the colorimeter. They know what the concentration is. And so then they graph that concentration against what the absorbance of the sample is. And then they create their graph in Desmos. So again, we are back to a more traditional patterns lab in the sense that we are going to have a mathematical model and a pretty simple one at that. So it's kind of nice to be, easing back into easier relationships than maybe what students have done in the previous couple of units. And then they're going to use that mathematical model to calculate the concentration of their unknown. So when they put their unknown into the vernier colorimeter, it's going to tell them what the absorbance is, but then they will have to put the absorbance into their their mathematical formula to be able to figure out what the concentration of the unknown sample is. And so once they know what the concentration is, then they compare it to the EPA allowable level, and the concentrations have been written out so that the unknowns always lie above what the allowable level for the EPA allows for those contaminants in the water. And so then students write a conclusion for this particular lab. And in this conclusion, earlier on in the project, when they were originally identifying what contaminant was in their sample, they were given a map of different locations around the area in which they live. And, that these are the possible sites that the water samples have come from. And so now they're using this information and the information that they learned in part one to really make a claim about where this water sample likely came from. They're going to use their qualitative data, they're going to use their quantitative data as evidence, and then they're going to provide reasoning that came from their research that they did in part one about where these, substances come from and the effects that they can, the negative effects that they can have on the environment and human beings. So that's kind of part two. And I would say that one probably takes a couple of days to kind of get through part two because, hopefully on day one, you have students collect their data, but then you're going to need another day to come back and, analyze the data, graph it, have them figure out what their concentration is, compare it to the EPA. And when I say 1 day, we are on 90-minute blocks. So, that would be 180 minutes. Okay, Matt's put in some pictures here and is going to share a little bit about these with you.
Yeah. So, and just this is showing the overall process for the Beers Law Lab, and we'll mention this in some of the future slides. But the team that I'm part of at Springfield High School used the patterns materials, and then also worked with a water quality scientist to modify the lab a little bit. But this is what ours look like. We use copper, phosphates, and nitrates, and we use the Hawk packets for each of those. And so students would have beakers that would have 4 different concentrations of for copper, for example, copper chloride. It's colorless, and then they go through a process of using these packets. And I love seeing just like the spectrum of how dark it is, and then they put each of those into the colorimeter, measure the absorbance. So this is just what the Beers Law physically look like for students. And then so I agree with Joe May, like for us doing this lab took a full day, and then like the writing and analyzing it took the next day.
And there is quite a bit of prep for this part of the project, because remember that each student group, and you would double up groups, but you know, if you have 4 different contaminants, you're going to need 5 different concentrations for each one of those contaminants. So it is a lot of solution prep. If you have multiple teachers teaching the course, you know, what we try to do is we try to all work together to prep those solutions. One way that we do save money, so the pictures that Matt has here is of the copper chloride, and that's colorless. So then you need to add the complexing material. We just use copper sulfate because that's something that we have on hand already, and we make it more concentrated so that it's blue in color and that the colorimeter will be able to detect that. But then we kind of, you know, fib a little bit and tell students that it's at a lower concentration than what it actually is. But that allows us to save a little bit of money of not having to buy all of those complexing materials and then thinking about, you know, how to get rid of them as well.
Yeah. The next slide shows, if you want to go to that, shows an example student or the data sheet. And so uh, this is one that students are, each team has their own little section of the chart. We zoomed in on one of the examples for copper. And so as Jermaine said, 4 different concentrations, and then at least for us, including 5 if you include just deionized water, like your control, and then the absorbance values that the teams measured with colorimeters.
And Matt and I were talking about earlier that we do really like to use these Google Sheets where you can see everybody's data at once, because it really allows you to kind of keep an eye on the data, and you can see very quickly if a group is, you know, maybe not on the right wavelength on their colorimeter or something, like something's going wrong with their data collection, so that you can know that you can go over to that group and kind of help get them back on track before, you know, they're done collecting all your data and then you finally notice that, you know, their data is not high quality. So we're at the point now where I think for most of our labs, we have a Google Sheet where students are putting all of their information in that. So it's a little bit easier to, instead of going to each group and having to check individually. All right, then that brings us to part 3 of the project. So in part 3 of the project right now, students are researching a solution of how to remove their contaminant from the water. Again, they are trying to think about removing this contaminant from a pretty large body of water, because most of the sampling sites usually on the map are like a river or a lake or, you know, something like that. So it's not like this is just a home treatment of water. You know, we don't want to use reverse osmosis or something like that. It's just going to be too cost prohibitive for this volume of water that students are trying to think about removing the contaminant from. So we want them to utilize their knowledge of chemical reactions and, you know, combine that with research to come up with what's the best way to remove this contaminant from the water, considering the source. Usually here we want them to include a diagram that's showing how to remove the contaminant and explaining the chemistry behind why the solution works. You know, for most nitrates and phosphates, the best type of removal is going to be biological removal using bacteria, and that does present a series of different reactions. And so I always feel like, you know, for us, this comes at the end of the year, and that's always a nice kind of transition for them also into biology to start, you know, thinking about how, you know, physics, chemistry, biology are constantly fields that are all working together to solve real world problems like having clean water. So when they're looking at the different solutions, they of course want to weigh the pros and the cons of the solution and then kind of put forth what they feel is the best solution. And then they want to indicate like an economic or environmental impact of the solution as well. And so this is kind of the culminating part of the project. So our wastewater service here is Clean Water Services. And so I've worked with them for many years, and they are great about letting us come to Clean Water Services for a field trip. They talk a lot about the biological removal of phosphate and nitrate there. You know, their water gets discharged into our local Tualatin River, you know, which most of our students here around us have been on. And so, you know, I really encourage you. This is a project that has a lot of great opportunities for career connections and for real, you know, real world experience when students are thinking, well, you know, I kind of like chemistry, but you know, what are some jobs that I could have with that? And Clean Water Services and all water service entities, you know, they need people that have an, you know, AA all the way up to people that have doctorates. So they have a very wide variety of different education levels that work for them as well. All
Cool.
right.
And then you can keep with the screen sharing if that's okay, Jome. But I'll just say, so we put on this slide links for you of the patterns files for the water quality project. And so that's the link on the top left. And then also, since my team at Springfield used those materials, but also made some changes, I just linked in the way that we did this project. And so I'm hesitate a little bit to have it duplicate for you, but you can also see just like how, one particular team kind of use those materials. And then a little bit, if you don't mind going to the next slide, we actually have we have a water quality expert or a water quality scientist here in Springfield who has a grant that helped provide a lot of the materials for us. So I know not everyone has that, but then also was really a consultant for us in this project. So it's hard to see the picture that says Summerfield Watershed. She designed this for us. She actually drew it on paper as more of kind of like a whodunit sort of thing. So students had the second part of our project works, or maybe I'll just back up. Day one was the Beers Law Lab, and then day two was them finishing that, analyzing that, and then doing research, kind of like Joe May described. For us, we had them make like physical posters about each different contaminant, including where it comes from, potential solutions, and then this is also where they recorded their constant from I'm trying to think what we call it. We call it their absorbance constant, but the constant that they would need for determining the concentration. In day three, different teams got samples that we had prepared from 5 different locations on our map. Summerfield, by the way, is kind of a joke or a play off of Springfield, which is the town that we're at. And so many of the different sites would test positive for multiple things. So for example, if I remember right, site 1, the stormwater pond tested positive for everything. And then site 2, I think it tested negative for everything. And one of the things our water quality scientists wanted us to teach students about was how stormwater ponds are used to filter um, pollutants. And so anyway, so each different site, each team did tests on different sites. And we tried to make sure there was a duplicate. So there was at least 2 teams studying each site. So in some classes, teams would do tests for 2 different sites, if that makes sense, so that we could have duplicates. And pretty much every class, we'd have a couple conflicting results. And so it was really helpful to have multiple teams do those tests. And then day 4 was them kind of putting it all together. So writing about their results, but then also potential solutions. Our kind of theme was that they were presenting a report to the city council where they were saying where did each of the pollutants come from, and then what should the city council do to fix it? Like how should they clean it up? So
I like that. Very, very real world. So
yeah.
I mean, definitely we would advocate that you reach out either to your wastewater agency that is local to you or your, city water entity. Many of these places have certain funds that have to be set aside and used for education. So, if you can make that contact and figure out who that person is in your particular area, they might be able to have you have field trips. They might be able to help you get supplies. But it's definitely a good connection to make. Maybe they might be able to have, visitors come and talk to your class about, different jobs that they have in water quality. So, and then
And
Matt, there was
I want
something,
to
yeah, you
Oh
wanted
yeah,
to.
oh good. Yeah, I want to add to something else too, and just in relation to that. So the person that helps with our schools in Springfield is funded specifically through our local utility. It's called the Springfield Utility Board. And so, but she was actually able to provide all of the like hawk packets for us, and then she takes care of the waste. So 2 of them have to be taken to our local hazardous waste, and that's definitely a trade-off and something like to consider with the materials that we're using. But she also would be very helpful to help either make connections, as Joe May was saying, or even support. She offered that she could support teachers by talking to you on Zoom or answering emails to help with kind of the setup of this. So at the very last slide, when we get there, we'll have both Jome and my contact information, and I would love to help if this is something you're interested in learning more about or getting more resources for. That's something that I would love to help with.
Okay, the last thing that we're going to discuss before we go into question and answers is we're just going to take a few minutes to look at the assessment examples and the rubric. So if you click on this link, again, this is a teacher file, so you have to be signed in with whatever account you are connected to on the Patterns website, but I'll just go ahead and show it here. So I did a little bit of revision on this particular assessment. We are going to have some professional development tomorrow night. Matt and I will be joining a Zoom, as well as all the other Patterns teachers, about implementing three-dimensional assessment. So again, I anticipate that this will change a little bit, but some ideas I wanted to throw out, or at least put out some ideas that were really aligned with this particular NGSS standard and like what was being asked for in the evidence of the performance expectation. So one area that I found that there was a big focus on was for students to be able to not only just balance the reaction, right, but to be able to show that on the reactants and the product side that we have the same amount of atoms, but that they're arranged in different ways. And so even though the standard is saying construct an explanation, I really felt like, and you'll see the construct the explanation more towards the end, that a more accessible way for students to do that is to be able to model that and to show that. And so I think when Matt was talking to you earlier about the PhET and the follow-up practice problems, I think that follow-up practice would very well prepare students to be able to then draw little molecules and show what's happening to these particular elements, and how are they rearranging going from the reactant side to the product side, and then also how can they total those up to show that the amount of atoms on both the reactant and product side is the same. So that's something that's very much emphasized in this particular performance expectation as far as conservation of matter is concerned. Another thing that is a big focus in this particular performance expectation is being able to identify the patterns of elements rearranging to form products. And so there's kind of just a little matching section here where students have the ability to be able to kind of match the reaction type to what kind it is. Obviously, this is a very low level of understanding or whatever, and so as we go to the rubric, you'll see that this is on the lower end of the scores. But I always feel like we have to have a variety of different questions that are accessible to a variety of different learners. You don't ever want a student to take an assessment and look at it and say, I don't know how to do anything on here, and so I'm just going to give up and hand it in blank. So, got to have some different levels there. But the main focus of this performance expectation is for students to predict what the products will be, but then eventually we want them to be able to, just like they did in the lab, explain why the products formed that way. So in this part, that's a little bit more accessible before they're writing the explanation, is to just identify, okay, what elements are involved in this type of reaction? What's the difference in the electronegativities of the elements that are recombining? And so it's kind of stepping them into the explanation. And so what kind of bond will it form? And then showing how those elements will come together in a Lewis dot structure, right? That's going to bring in the valence electrons and allow students to either show the valence electrons being transferred or being shared based on, what they determine the electronegativity difference to be. So something similar here, but just with a different type of reaction. And then kind of at the end, I feel like building to the crescendo of constructing the explanation. At the bottom here, we have a couple different examples of, now how you can kind of up the rigor and have students, write out reactions, right? So this question is having students write out the reaction just from the description, first of all, and balance it on their own. So it says draw a model, but in this case, it means a balanced chemical equation of these two different types of reactions that have to do with sulfur gases forming sulfuric acid in the atmosphere. And then from there, after they've written out the reactions, then now we want them to construct the explanation, right? So again, that they've kind of shown those pieces individually previously in the assessment, but now they're really trying to put all of those together in an actual explanation. And then I really wanted to wrap back to that conservation of matter idea about how do these reactions kind of play into that conservation of matter? And so Matt was talking about earlier that they would have practiced with the nitrogen cycle. So since these questions were about the sulfur cycle, I put a picture of the sulfur cycle here. And then this kind of last follow-up question about the conservation of mass is just asking students to talk about one pathway on the cycle here and how the burning of fossil fuels is going to impact, whether we're going to have more or less of these reactants or products that we see in this one pathway, right? Kind of getting back at that Earth is a closed system. And so as we create more of one thing, then that means that there's going to be less of something else because the reactants are becoming the products. So that's one kind of option for kind of building to that mastery level. And then I had another option here as well. So earlier in the year, Matt and I got to meet with one of Matt's friends that is very involved in climate science. And one thing that Ian was very adamant about was that we make sure that students understand what is going on with the pH of the water in the ocean and how that is being impacted. And I think this assessment is a great opportunity for students to be thinking about that. So this question is setting the stage for the fact that, already they know carbon dioxide is increasing in the atmosphere, but one of the stations in the predicting products lab has them actually blowing carbon dioxide into water that has universal indicator in it so that they can see that it's becoming more acidic. So again, this is, more mastery level. Students are writing out the reaction and balancing it on their own. And then they are, constructing their explanation about how that carbonic acid would be forming in the ocean water. And then the follow-up this time, instead of it being like a nutrient cycle, would be about what's happening to the pH levels in the ocean and how could that then affect organisms that have shells, which are made of calcium carbonate, which again was a idea that was presented to them, but in a different form in the predicting products lab because it was a building, not an actual shell on an organism. So again, those to me would be more mastery level questions, but kind of building to what that performance expectation is hopefully asking for. But I definitely anticipate that we will make some revisions to this based on what we learned this week. So that's a little bit about the Unit 5 assessment. And then there's also the link to the rubrics here. There's rubrics for all of the task sets, I believe, at the bottom. This one's taking you right to the assessment rubric. But again, you can kind of see how those knowledge and skills are kind of building over time and how, earlier on at the lower levels of proficiencies, we're just looking for kind of pieces of those. And then as we move more towards the mastery end, then we're looking for students to put all those pieces together. And again, meet that performance expectation that's been set out for them by this NGSS standard. Okay, that was perfect because Matt and I wanted to end by 5:50 so that we had time for questions at the end. I'm gonna stop sharing now. Or no, I guess I do still need to share our questions.
Sure.
So let me go forward one. Okay.
Maybe I'll summarize. So the attendance link, again, if you haven't filled that out, it's like one last chance. And then two things. Well, also Joe May and I both put each of our emails. And so please feel free to email us if you have questions that come up. And as I mentioned, I would love to help make more connections about the water quality project. So if that's something that you're interested in, and the person that we worked with offered additional support in that. In the chat, I would love to get some feedback on how this went for you. I think actually Joe May would know, is there a like survey that they do through Portland MetroSem partnership?
I was not
Or...
sent one this time.
Okay,
So.
well then don't worry about that. I would just love some feedback, or we would love
Yes.
some feedback. Either could you answer any of these questions? So either one is, what was the most valuable part of this webinar and why? Or number two, do you already do a water quality projects? Are there any additional support you need if you don't and would like? Or what other questions do you have? And so I'm just going to think of this as a menu. Could you choose one of these things to put into the chat? If you'd like it to be a private message, you can totally do that too, if you'd feel more comfortable. And then other than that, I think Joe May and I are done, and we would love to stay and answer questions. I know there was a question earlier about Unit 5 and Unit 6 about including stoichiometry with this. And so if you would like to ask that again. I think Jo May is a better one to respond to that.
You're welcome. Thanks for coming tonight.
Yeah. Cool. Thanks, Jess.
Yeah. I know. I feel sad that we can't quite get into the details of every single task set, but I feel like we were able to at least do the equation sort tonight, which was great.
Oh yeah. Laura, yes.
Awesome. Thank you. I'll give you my email.
Please do. Yeah.
Thank you. Super helpful.
Um, and actually, Laura, maybe to make sure I do it, can you email me and then I will respond to that email with the link to our.
Yes, I just wrote it on your email. I will do that.
Okay, perfect.
Thank you.
Yeah. So, Jo May, the question from Shifra is, I'm curious about the differences between combining units 5 and 6 versus the individual. I wonder if
Yeah,
you.
at Mountainside, we teach units 5 and 6 together. It's just really hard for our team to think about separating stoichiometry from the rest of chemical reactions. So, we do that as a combined unit. So after we're done with like predicting products and conservation of mass, we kind of, give an assessment at that point, and then we go on to, stoichiometry. And then we do the water quality all at the end. So a lot of the stoichiometry problems that we have students practice with are problems that have to do with, air pollution or water pollution. So like we just keep that theme kind of going all throughout. And then we do the water quality at the very end. So, for us, this is the last unit of the year. We do units 5 and 6, and then, we're usually ending the year kind of at the end of the year doing the water quality project. So I definitely think it can be done. I think definitely you'll want to take some kind of midpoint along the way, because trying to give students like a test or an assessment on, balancing and predicting products and stoichiometry would be a lot. So I think breaking those two pieces apart at least will make it more manageable for students. But I think you can definitely keep the phenomenon going throughout both of those units and not have to start with a new unit opener and a new, set of task sets. So.
Cool. Thanks.
Yeah.
I gotta go, but thank you so much. I'm sure our teams from
Hi,
McMinnville will be
Jess.
in touch. Hi.
Okay, sounds good. Thanks.
See you. Bye.
I'm enjoying
Thank
reading
you.
these things too. That's cool, Pam, that you're out of worked at
Yeah.
wastewater. Where's in Mac? Oh, in McMinnville.
Oh.
Sorry. Yeah.
Yeah.
McMinnville.
Cool.
That's awesome.
I know. I wonder, do you think there's a chance to make connections with people there that
Yeah, Pam, you've got an inside.
I know.
Yeah,
You already know somebody there.
Laura actually, I think she's gone now, but
No, I'm
oh,
here.
you're still here. You do wastewater stuff.
Yeah, I have my students, we go up and see the wastewater treatment facility, same kind of thing, and they're really awesome. I mean, I teach AP environmental science, so I've done it in that class.
Cool.
I mean, I remember when I first started doing this project and I'd ask kids where the water went when it went down the sink, and they were like, to the ocean. I was like, the ocean.
I know.
I think this
This-
is like one of those citizen science things that like really everybody should know where their water goes when it leaves their residence.
And where it comes from in the first place, like how it
Yeah.
gets treated before you get there. I'd say for ours is through our local utility board, and she has funding for, like, she just we met last week and she just told me that for the people that give her the funding, they just love that every single student at both of the high schools in Springfield, like every single student does water quality testing, and then is thinking about, how do we clean our water, and then what are the things that pollute our water, like just that. Yeah.
Yeah, that's awesome. I think it's great if we could get all the chemistry students out there. It'd be great.
Yeah, they're so friendly too. I know.
Oh,
Yeah.
thank you.
Yeah.
That gives me, we actually have separate funding for doing a whole class workshop. So we're bringing all of our freshmen to Oregon State University this year, and our juniors in biology do like an ecology field trip, and we need to come up with something for 10th grade. So I didn't even think of the water quality treatment plant, like actually going.
Yeah.
That would
Well,
be
and I know
perfect.
at least a Clean Water Service is part of the reason that they are really trying to do a lot of outreach, is that they're you know, their staff, so much of their staff could retire, and they're like, we're not having people like go into these jobs, and these are jobs that like we need people in our own community to get trained to do these jobs that want to stay here. And so it's really important to them. And like I said, there's a whole variety of different education levels for different jobs
Yeah.
at, you know, clean water services, and good jobs, right? You know,
Really good jobs, good paying jobs.
living
Yeah.
wage jobs. So
Yeah, for sure. Well,
Yeah.
thank you all.
yeah.
Thank you
Welcome.
so much. It was awesome. Always
Yeah.
appreciate it. Take care.
Bye.
Bye.
I guess, thank you so much. I'm actually in Massachusetts, so this is like,
Oh, thank you for,
Oh,
it's late there. Thank you for joining.
I
us.
know.
yeah. And like, I'm definitely an island. So I teach in a private school, and I was using iHub before, and someone in my iHub group was like, they like patterns. And so now that I'm teaching honors, I'm trying to make it more rigorous. And I definitely already do like the transfer tasks as my assessments. So I like that your assessments are getting more into that application, which is exactly where I want them to be. And I was looking, do you know if there's any plans to like do unit 8, like the acids and bases ever?
I know that it's said that it's under construction for a long time. Like we just never get there. So I know like I'm not really a person that would be a great candidate for helping to develop that, because, you know, usually we end at 6, but I feel like it's like Christy and Andrea, who are part of our council, that have really talked about working on those, you know, on that particular unit, because it's just been said that, you know, it was going to be developed for a couple of years now, and it's just not happening. But unfortunately, both of those people now, they are not teaching chemistry in the classroom anymore. One's a TOSA and one is teaching, but like totally different, you know, assignments besides chemistry. So I really have no idea when that will be, you know, developed out or whatever. Maybe now that we've had Matt join our council, and also another person, Nessima, and I think Nessima teaches AP also, and would probably have more experience with, you know, already teaching those concepts. So, you know, perhaps that could be something that people work on, you know, over the summer or something like that.
Yeah.
Yeah.
My guess is not for a while. Like we're not very close, but my background prior to patterns was through through modeling chemistry, and there's so much overlap, which is awesome. So we had a similar thing in modeling chemistry where the units that kind of start crossing over into AP were under construction / not developed, but they're
not as
so
developed.
I could look if there was in modeling chem, but
What's interesting too is where it looks like the unit 8 is going is very much in line with like what iHub and now Open Syed is doing, is the
Oh, yeah.
oysters as the phenomenon, and like that ties into how you all have put together for the labs with the blowing bubbles into the right. So like they pull that in, and I was gonna swap out one of the double replacements to be more green with like a calcium chloride and sodium carbonate, because that's how oysters make their shells. And so like if I can get to acids and bases and pull that back in, and
Yeah.
they do like experiments where they see how adding hydrochloric acid, when you add those two together, you no longer form the precipitate. But
That would be great. Yeah.
yeah.
Yeah. I mean, Matt and I were talking about this earlier too. We feel like it's better for students to keep cycling back to ideas, rather than us to have this fallacy to think that like, oh, because we taught it to them one time, now they're going to just know it forever. You know, more times we revisit it, the more likely they will be to remember it. So yeah, but we will definitely, we're meeting as an all council Saturday also. We will put that out on the table for people if they are help develop that would be a good thing to get going this year.
I appreciate like being able to like find you guys and you guys having this. So I'm happy to connect anytime. Thank you so much for all this. I should let you all go.
Okay.
Yeah. Well, thank you for joining us. Like I said, late back where you are. So
Thank you.
Yeah, well, have a great evening.
Thanks, you too.
Okay, bye-bye.
Bye.
Well, Matt, we did
Thank
it.
you. I know. I feel way
It was
better.
great.
I think so too. I have a quick debrief. I was gonna say
I'm gonna stop the recording.
oh, thank